Hope you guys can hear me and see my whiteboard. So I think today is Feb 21st, 2024. I think we might be on day 4, maybe. Okay, so in the last class, we looked at linked lists and how to reverse them. Or more importantly, we only saw how to reverse print a linked list. And I had asked you guys to try out how to reverse an actual linked list. I will put a pause on that, and there's a reason for it. I'm going to put a pin on it, and I am going to switch gears to something which a lot of people have been asking, which is this is the most important and the scariest thing for a lot of people, dynamic programming. And I want to address the elephant in the room early on. And there is a reason for that. If you look at any programming interviews, you will see that the number of problems you will encounter, 50% of them is dynamic programming, and rest all put together is another 50%. So the probability that you will encounter dynamic programming sooner or later is very high. So then I thought, okay, why not let's tackle it straight on and let's begin with it. In fact, you guys need to know very few things in it, and the most important thing you need to know, you already know. Take a guess what it is. So there has been this technique in the last 2 or 3 classes, which I keep insisting you have to know it in and out. It is not the most efficient technique, but I keep insisting you should know this. What is it? Please speak up. I don't have the chat window. Okay, Christopher says recursion, and that's perfect. Okay, that's perfectly the answer to it. So here is the reason why I keep saying that. Dynamic programming is defined as whenever you have an overlapping subproblems, okay, it should have, these are all technical terms. I'm just throwing at you just to intimidate you. Don't worry about it. I know I'm intimidating you if you haven't heard this before. It's called optimal substructure, second term, then memoization. Then if you have all these three, it's called a dynamic programming. And there is this concept called top-down versus bottom-up. So any of the standard computer science lectures you start in dynamic programming, they will start with saying, oh, your problem should have all this crazy theory, which is your problem should have overlapping subproblems, it should have an optimal substructure, it should have memoization. Honestly, dynamic programming is very simple, and whoever named it dynamic programming really did a terrible job, because it's neither dynamic nor programming, and we'll see why. To start with, optimal substructure is what you know otherwise as recursion. Okay? So my goal here is, even though if you look at dynamic programming problems, it might look very complicated, everything is solvable by recursion. And at the end of the day, what dynamic programming is, it's a simple optimization on recursion. So remember, we already saw one optimization on recursion. What is it? In the earlier classes, we looked at recursion, and I insisted we remember this, but then I said, oh, this is the most inefficient thing. A simple way to do recursion is to do what? Okay, iteration. Hey, okay, okay, perfect. Iteration. Yes, you're right. So you already have the tool. Sorry, I can't do voice at the moment. Okay, all good, all good. I'm trying to keep that window open. All right. So yes, Chris, you're right. So this is optimization. So let me start with a sample problem. Like forget that we are in a class of dynamic programming. Let's ask this simple question. Fibonacci series. Fibonacci series, as some of you might know, or it's okay if you don't, is the series of numbers which is simply the sum of the previous two numbers. So 1 plus 0 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 2 is 8, 8 plus 5 is 13, so on. If you look at the index of it, Fibonacci fib equals this, index is this. Fibonacci, the 0th Fibonacci number is 0, first Fibonacci number is 1, second Fibonacci number is 2, third, fourth, fifth, sixth, seventh, etc. Now, I'm going to start with this question. Question 1. Write, oh, given index n, print its Fibonacci value. So what it is expecting is given 4 input, output should be 3. Given 6, the output should be 8, etc. Okay. And I will give you a hint. Okay, I will even insist this. Do it recursively. Just to remind you why we insist on recursion is the toughest and the most complicated thing. And it actually is the foundation of all coding, which originally people started writing everything in recursion. But then everything else in coding, you could probably call it languages, you could call it better algorithms. It's all an optimization on recursion. Okay, so I'm just reminding you, this is the reason why I keep insisting on recursion, because I don't want you to memorize anything. Anytime you think of a question, the first thought you should come into your mind is, can I do it recursively? I mean, like I said earlier, terrible idea efficiency-wise, but that is exactly computer science for you. For the last 50 years of computer science in one line is improve recursion. All right, so let's start with answer is write this Fibonacci series function. Let's write a function for it and do it recursively. So remind me, what are the steps of recursion, or any question for that matter? When we get a question, what do we do first? Anybody? No answer. Rephrase the question. Perfect. Paraphrase or rephrase the question. So we already paraphrased and rephrased it when we took some example values and we tried, okay, this is the meaning of Fibonacci. This is how we write it out. Or if he gives me 4, we should reply with 3. Okay. What is the second step? Okay, I'll answer myself. This is core logic. Then we said we should always keep in mind the edge cases or null cases. And then we are going to type it out in editor. And the last thing is dry run. Okay. So now let's think about core logic. Even within recursion, there are certain steps I insisted on. Does anybody remember what the first step is? Yeah, hi, Urvika. Hi. We are talking about dynamic programming. And what you missed is basically some of the terms in dynamic programming. And I was telling them most of the problems are dynamic programming. So it's important you start falling in love with it and start solving it now itself. the probability of you encountering is uh, very high. And this is like theoretically, this is what they call dynamic programming, which is overlapping subproblems, optimal structure, memoization, and a lot of these crazy terms. I will get to them all in a second, but if there is one thing you must remember, the answer is recursion. This optimal substructure is known as recursion. That's it, okay? Everything else we'll see. So now we are looking at one simple problem, nothing to do with dynamic programming. It's called Fibonacci series, which is given the number 4, you should print 3 because that 3 is the 4th number in the Fibonacci series. And we were just saying, paraphrase the same thing how to tackle a new problem, paraphrase it, core logic, write it down, pen, paper. That's what we're anyway doing. And think of the edge cases while you write it, type in the editor, try run. Okay. So recursion, like I insisted you should use recursion. So what is the first thing we do in recursion? Or for that matter, what is the first thing you should do in any problem which asks you to write a function for it?
I was saying base case, but I know that's wrong. Like,
Okay, so yeah,
think about
that's
the base
fine.
case first.
Yeah, but that is gonna come only as step 3.
Yeah.
Case
Yes.
in recursion especially. The first one is always the function signature. Remember, to remind you, we are doing it in Java, but that's only because it will force you to think of function signature. Second one is the core logic. If you remember, it was if someone gave you everything before me is done, what will I do? What will I do? That is a core logic in recursion, base case, and that is your exit condition. And by the way, a parting gift, which if you remember was nothing but copy paste the same function signature inside your code. So let's try that, right? So let's try public static, right? I don't know what my output is going to be. I'll leave it there. And my function is fib. I know the interviewer is giving me a number n. So now your goal is to just print the Fibonacci value. So remember, as you can see, I haven't even returned my output data type yet. So let's start. We wrote the function signature. Okay. Core logic. Core logic is 0. This is the example of core logic in Fibonacci is 0, 1, 1, 2, 3, 5. Let's say you are sitting here. Pick a number in the middle. Somebody tells you, just forget everything else. All this is done, right? Let's also write the index of it. 0th index, first index, second index, third index, fourth index. You're at the 4th index and somebody told you, assume that you already have the values of all the Fibonacci numbers before index 4. What will you do? You are the person who is controlling the number 3. What will you do?
I will sum up the values, 2 values before me. Like,
Perfect. So how do you sum up the 2 values? Let's say sum of n minus 1 plus sum of n minus 2, but not even sum. Hold on, that's a bad way of writing it. So I'm telling you that n minus 1 and n minus 2. Okay, so this is all me. So me is equal to sum of my father and my forefather, grandparent. Okay, so this is our core logic done. Right now, base case. Base case is when we hit all the way here, what do we want? Can I say if n is equal to 0, just return. So now I'm thinking, oh, wait, I don't even know what I'm returning. Let me think about it. Oh, I just have to return the the integer value because the input was 4 and we are supposed to return 3. Okay, so in that case, I realized, okay, it's a good idea. Let's return int, right? So if that is returning int, if n is equal to 0, which means my index is 0, what should I return?
0.
0, okay. And remember, when we are going back, we should always think of 2 people before us. So when you're here, you should also think that not only will this guy 0 be the base case, 1 also can be the base case, because that is the base case for 2's grandchild, right? So we also need to think of if n is equal to 0, can I say return 1? Okay. So we did the third part, base case and exit. Now, finally, parting gift, right? Parting gift was copy paste exactly what you had before in the signature and send it to your children, remember? So the simple answer is just put fib return. Done. That's it. See how simple it is to write a recursion. Just to remind you, never ever think of opening up recursion. That's going to mess you up. If you follow exactly these 4 steps, you're good to go. Okay. So now, clearly, this is a terrible solution. Why? Or rather, if I ask you what the time complexity is, can you tell me what the time complexity is? Okay, let me put it this way. Let's say you are asked the FIBO of 4, right? You're at 4. You need 2 things. What are these for FIBO of 4? Remember, you're at this number here, FIBO of 4, and you are trying to find the answer of FIBO of 4 is 3. So this is the same question I asked earlier, right? So what do I mean by to give FIBO of 4? I need 2 things, which are
Fib of 2 and fib of 3.
fib of 3 and fib of 2, correct. Now, to do fib of 3, I need 2 things, which are, can I say fib of 2 and fib of 1? Okay. Fib of 2 needs 2 things, fib of 0 and fib of 1. And fib of 2, again, needs 2 things, which is fib of 1 and fib of 0, right? Now, let's go back to the original definition of dynamic programming. It has to be overlapping subproblems. Let's see what's overlapping subproblems. Now, if you look at this, you can see that fib of 2 is calculated here, and fib of 2 is also calculated here, right? But in the brute force case, which is recursion, you are calculating it every single time, right? So let's say if you are doing fib of 4, your control comes into fib of 3, you go back in, so you're going here, your control comes back to fib of 2, and then control comes back to fib of 2 here. So fib of 2 has to calculate fib of 1 and fib of 0. The control comes back. Remember recursion and stack frames? So you can even, to ensure we make it clear. So this is main. We had 1 stack frame in main. First time we are asked fib of 4. Fib of 3, we have new stack frame created for fib of 3. We have new stack frame created for fib of 2. Another stack frame created for fib of 1. Right? And when we hit fib of 1, we are reaching the exit case, which is if n is equal to 1.
What's up, Javier?
So when you return this, here we have the value 1, right? So now what happens in the case of stack trace is, this is done, it returns the value 1. Fib of 0, same thing, it calculates and returns the value 0, right? And fib of 2, as per our definition, is just summing fib of previous 2 values. So we are already at fib of 2 equals 1. And before the control goes back to my parent, I have to also do the second part. Remember, we are just doing this now, which is from fib of 3, we are doing fib of n minus 1, 2. We have to still do fib of 1. which means now here another stack frame is created and you do fib of 1 again, right? So in this case, it's a simple operation because fib of 1 is already returning. You hit the number, you return 1. But let's imagine that here. If the control goes back to fib of 3, right? So fib of 3 is the sum of fib of 2 and fib of 1. And we know that is 2. Fib of 2 is 1 plus fib of 1 is 1. So fib of 3 is 3. Is it right? 0, 1, 2, 3, 2. Okay, so there's a 0 missing. But anyway, the point is, when the control comes back to fib of 3 is done, the control again goes back to fib of 2. And it's going to repeat this whole sequence again, fib of 2, fib of 0, fib of 1. That is, it is very inefficient. Or in other words, if you're given a tree like this, and we will talk about this when we get to the trees, but generally you might have seen this question that if you're given a tree of height n, or the number of nodes is equal to 2 power n. So in fact, in this case, we have 2 recursion back to back, and it is a hot mess. And I will show you how that happens. So let's actually code this up. Right? Go to the Zoom. Stop sharing. Okay. Let me share this guy here. Online GDB. Okay, just gonna code this up. First thing we do, same thing, same logic. We write the function signature, and our brain is already primed for this because we just wrote that in paper. So fib of int n. Core logic is return fib of n minus 1 plus fib of n minus 2, 10. The exit condition is if n equal to 0, return 0. If n equals to 1, return 1, and done, right? So now if we put, let's say, int out is equal to fib of 4, system.out.println out. Let's read it out loud. Int out is fib4, semicolon, system.out.println out. Looks good. Public static int fib. Int n, if n is equal to 0, return 0. If n is equal to 1, return 1. Return fib of n minus 1 plus n minus 2. And let's print. I dream of a day when the code will run the very first time in any language, which is, of course, it takes years of practice. All right, so fib of 4 is 3, right? So let's write it again. Fib is 0, 1, 1, 1 plus 1, 2, 2 plus 1, 3, 3 plus 2, 5, okay? And the indices are 0, 1, 2, 3, 4. Fib of 4 is 3, that's correct. Let's see what fib of 5 is. Fib of 5 is run. 5, okay. So it's doing its job correctly. Now, but more importantly, what I want to show you is, let's create a global variable, or in Java, it's a static variable, static int count equals 0. And I'm going to say count plus plus. And I'm doing this just to count the number of times the code gets inside this function again and again. I'm going to say fib out here. And the reason why I'm saying this is I'm just going to print system.out.println a couple of things. One is my n, which is the input value, is n plus fib value, that's equal to plus, what is the fib value? Fib underscore out plus counter, okay? Count equals plus count. It's a system.out.println n is equal to n fib equal to fib underscore out count, it is equal to counter. Thing. And we won't print this because you're already seeing the fib, right? So let's run this and see what it prints. Again, sorry, it shouldn't be inside the main, should be outside because it's a static sum. I dream of a day when everything will run on step one. What am I missing? Class main, public static void main, 23 missing. What did I miss?
About you need to return something in fib function.
Yes, sorry. Good point. Thanks. Okay. Cool. All right. So you can see that here, just for 5, it's already gone inside the function 15 times. Let's try something else. Let's for 10. Okay, for 10, it's gone 177 times. Let's go 30. See what's happening? Just to get to fib of 30, it is going all the way to 2 million. It will go to 2 million close to it. See what happened in efficiency wise, right? So this becomes such a complicated thing because we have 2 recursions in next to each other and it's going crazy, right? So sheer number of times the code gets into that function. So like my point being, clearly recursion is a terrible thing to do, right? So while it is printing this, it's gonna take a while. Let's go back to our screen, whiteboard. Share content, screen, to broadcast. Okay. Share content, screen, start broadcast. Okay. Okay. So my point being, clearly, recursion is a terrible thing to do, right? Now, let's talk about optimization. So in this case, what is a good optimization to do? Any guesses?
We are doing repeated work. Like, for example,
Okay,
fib2 is calculated 2 times in the current screen. Like,
correct. So the first thing that struck you is, oh yeah, this is repeating work, right? This guy here, if you go back to the definition of dynamic programming, we already saw that the optimal substructure is a fancy word for recursion. We already saw the overlapping subproblems, which means we are doing the same job again and again. Third thing is memoization. Again, it's a stupid word. It simply means, how can we not do this overlapping problem again and again? Okay, what is your logic and what's your intuition telling you?
we can save the result somewhere.
Perfect. You can save or store the result somewhere. Okay, somewhere. We call it a cache, and cache is a term used for anything we sit on RAM and do it on RAM. It's a cache. Now, what exactly used for cache? You could probably use an array. You could probably use a hash table and things like that. Let's start with the fact that let's store everything in the array. So I'm going to say here first, I want a new array. All right. Yeah, actually, let's make it static. So let's say I have the fib function here, public static int, the same thing as before, but I want to keep something outside it. Like I'm just going to call it static int cache equals a new array of 100. Again, you don't have to write it in Java. You can write it in, I will insist you write it in Python eventually, but this is, at this point, we are training our brains to do this. Okay. So, okay, we have a cache, and remember, it's not a good idea ever to have global variables if you remember that from your classes, but that's okay. For now, I just want something sitting outside this function, and I'm going to write the same thing again in 10, okay? So now, first thing is, we are again going back to our core logic, but our thought is, for fib of 3, if fib of 2 already exists, we just have to return fib of 2 from the cache, find if fib of 1 already exists, sum them both up, and that'll be fib of 3. But more importantly, when you are asked for fib of 4, what is the first thing you should check?
If I already have the result or not, saved somewhere.
Yes. So the first thing is if, we should also like fill this up with some values. I'm going to say for in I equal to 0, I less than cache dot length, I plus plus. Let's fill it up with cache of I equals -1. Like it's just priming or initializing your array with some random number. First thing you check is exactly what you said. If the n's value, the corresponding value for n is, if it's not equal to -1, so this is, remember, leap of faith, your brain is going to say, no, but it might not be -1, blah, blah, blah. Don't do that. Just a simple answer. If cache is n-1, cache of n is not equal to -1, just return cache of n. Simply put, if somebody asks you fib of 4, and if fib of 4 itself exists, just return fib of 4. Okay, and your brain is going to say, no, but it doesn't exist, blah, 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 blah. It's okay. Just ignore it. Now, remember, our core logic was fib of n-1 plus fib of n-2 is me. Okay. Now, what do you mean by me? So if as soon as you get into this function, there's an if condition here. Let's say initially when you come here, your cache is just -1, -1, -1, right? And you want 0, 1, 2, 3, 4, fib of 4, right? So the first thing it comes here, oh, cache is not equal to -1. Oh, not going to go there. So clearly we need an else here. Else is if the cache is still -1, which means the value I'm asking for is not there in the cache. Remember, the same old logic. You're a person sitting in the middle of this, and you are told that, hey, here is the value 2 and 1. What do we do with it? We just sum them up, and that's what we did. Only different this is, instead of me is equal to this, and earlier, if you remember, we were doing return fib of me and my 2 children, right? My child and my grandchild. Now, remember, we have our value, we have a cache sitting for us. So where will we store it?
In the cache.
Okay, cache where? In the cache, it's an array, right?
N.
N. Cache of n is fib of n-1 plus fib of n-2. Honestly, you're done, right? So you remember our logic initially, like we are going back to same recursion logic. Function signature core logic is done. Oh, base case, fine, base case. Base case, okay, so we need a base case, which is, so if, same thing, n equal to 0. So what are we doing? We started with 4, we went to 3 and 2, and for 2, we need 1 and 0. And at that point, we can simply say cache of 0 is 0. So we have to initialize this to initial values. Same thing. And I'm saying 2 values because in this case, we need two base cases exits, right? Yeah. n is equal to 0, cache of 0 is this, n is equal to 1, cache of 1 is 1. And we are hard coding it literally. Right? So see how I took the same logic for the exit condition in our recursive form. Where'd that go? The same exit condition. Now your brain started saying, oh, hey, I don't want to return this. I want to store this thing somewhere. Okay, so all I'm doing is taking that and storing and hard coding it into the cache. That's simply an array, right? If n is equal to 0, it's a cache of 0, n is equal to 1, cache of 1. And remember, our parting gift is just sum this already, which we are already doing, right? Now we can probably just make it slightly more interesting and optimized. We can put some if, else, and if for all that, so that remember our goal is optimization. Dynamic programming is nothing but optimization. So we can simply do this. Let's put if else, because otherwise it's going to run all these things again and again, right? So if n is equal to 0, we do this. If n equal to 1, we do this. So the control doesn't have to do this every single time. If we are not n of the n is equal to 0 or n is equal to 1, we just fill up our thing and simply put, when we are leaving, we just return it. Return. This is a catch all cache n. You'll most likely not get here, but you have to write a return at the end of the function. So let's go back here. So what all did we do? We wrote the base case, yes. We wrote the signature, we wrote the core logic, we wrote the base case, we even wrote the parting gift. We paraphrased the question, we wrote the core logic in pen and paper. We already thought of the two edge cases, which is in this case, the exit conditions. Type in editor. Before that, let's even do a dry run on pen and paper itself. Let's say we are starting with 4. Okay, so the 4 comes in. N is equal to 4. The very first thing is when n equal to 4, it comes to the cache, which your cache is now currently empty, or the definition of empty in our case is we have a cache which has just -1, -1, -1, -1, -1, 0, 1, 2, 3, 4. Okay. The first check is if cache n not equal to -1. Is cache, okay, no, its cache is -1. Okay, so we don't go there. We go here. Else, is n is equal to 0? Nope. N is 4. Is n is equal to 1? Nope. Else, cache of n is fib of n minus 1 plus fib of n minus 2. Right? So now we just got into the recursion call. It's going to go deeper and deeper from here, create newer stack traces. So let's say we are at fib of 3, because you had to get fib of 3 and fib of 2. We are going in with 3 again. 3 is cache of 3 not equal to -1? Nope, cache of 3 is -1. Is n 0? No. Is n 1? No. Okay, so I need to fill up cache of 3, so which means I have to do fib of 2 plus fib of 1. So fib of 2 will do the same thing, but it still is -1. Fib of 2 is going to come here, -1. It's not, so we are not going to go in here. Is n is equal to 0? No. Is n is equal to 1? No. All right, so now we are back again. I want fib of 1 and fib of 0. Right? Now we're going back in with 1. Remember, the value of 1 is still -1. So we go in there and we say, okay, is cache -1? Yeah, we're not going to go in there. Cache, and if n is equal to 0, no. N is equal to 1, yes. So we go back and replace this value with 1. Oops, sorry, 1. And so we won't even get in here, right? Because we already found n is equal to 1, we return. So we are done with this, we returned it. Same thing for fib of 0, we come here, we check this. No, it's not, still -1, not going in there. N is equal to 0, oh yeah, sure. So in that case, we go back and rewrite this. We replace -1 with 0, right? And Now comes the interesting part. This is done, right? And we remember we are here. We are in fib of 2 is sum of fib of 1 plus fib of 0. So with this code here, we are going to replace 2, the minus 1 and 2, with 1 plus 0, 1. Right? So now 2 stack frame is done. It's return. You're going to return cache of 2, which is nothing but 1. Okay, so we are back. This is done. And we came all the way to it's the same colors at least. Let's go back to 0. We are done with 0. On the way back, we filled 0, we filled 1, we already filled 2. And why did we come to 2? Because 3 had asked me, or oh, no, wait, here. For 3, we had seen it needs fib of 2 plus fib of 1. Now we are coming back again asking, okay, my n's value is 1. If cache of n not equal to minus 1, oh, it's not minus 1. All right, cool. So I don't have to calculate this again. So we just got rid of, we never reached this place. We never had to go to fib of n minus 1, fib of n minus 2. Done, because we're just going to go back, pick this value. We know this value is 1. We know this value is 1. That's it, right? So on, you just go building it up. So this is what I call optimization 1. Now remember, in the interview, if the person asks Fibonacci of n is equal to 4, nobody is telling you to do dynamic programming. You should always go back to your fundamentals. Okay, let me write my solution 0, right? Solution 0 in recursion. And I want you to think, your thought process is what I'm trying to change. The recursion, okay, now let me optimize it, which is plus cache, aka memoization. Remember fancy words. Now, let's say the interviewer or you yourself think, wait a minute. Okay, let's even try copying this into the code, right? So I insist on showing you this only because you need to see the sheer amount of count it takes to get into that functions there. Okay, so let's see. Share screen here. GTV online. Let's see. See, just for 30, it went all the way to here, 1148,710. This time we are going to optimize it. Let me take a screenshot of this, right? And then let's add our modifications, which is we are adding static. So we are adding a cache. Remember, our goal is to add a cache now. One second. Okay. Yeah, let's go back here again. Static int. So remember, this is a nasty way of writing because it's global and stuff. In Python, you can write it just outside your main function. It'll work. But since our motto is to go into the basics, we're going to do this, right? And then we are going to go back. Same thing like we did before. The only difference is now we are, so the first, remember we already wrote the signature of the function. Now we are going to write the core, which is cache of n equals fib of n minus 1 plus fib of n minus 2, right? Now we're going to, first time when we come in, we're going to check if cache of n not equal to minus 1. So we haven't filled it with minus 1 yet for int I equal to 0, I less than cache dot length I plus plus. Let's fill it with minus 1 cache of I equals minus 1. So we have the first thing, remember when we come in, we check if cache of n not equal to -1, if it already is done, we're just going to return cache of n. If our job is done. Else, if n equal to 0, we're going to hard code the value, which is cache of 0. You can even put cache of n is 0. Else, if n equal to 1, cache of n cache of 1 bracket equals to 1. And okay, we don't need this exit conditions. We already finished that. Else, you don't need this else. You can try at home without all this else and if. You'll see the count will still increase. That's it, right? So we just have to return cache of n. Okay, let's see. Let me read this out loud. Static int count is 0. Static int cache equal to new int of 100. For int I is equal to 0, I less than cache outline I plus plus cache of I is equal to -1, filling it up with -1. Now we are calling the same thing. Int out is equal to fib of 30. Let's start simple. Fib of 4. Public static int fib int of n count plus plus, the same count as before. If first time if it exists, return it. Else if n is equal to 0, cache of 0 is equal to 0, cache of if n is equal to 1, cache of 1 is equal to -1. Okay, that looks good. Else cache of n is equal to fib of n minus 1 fib of n minus 2. System.out.println. Heck off, it will just put a new line there. Okay, let's see. So let's try running this and see what happens. Okay, what am I missing for in click startup type? Let's not do it there. Just fill it up here. One time it did not read it. Sorry, fib_out doesn't exist. So we don't even need this guy now because we are just focusing on the count. Let's see what the count goes like. Story of my life plus count equals this. Did I get everything right? Plus count. All right, so count 7 for 4. That's decent. Let me take the screenshot of the previous guy, right? Let me go find where this guy is. So we had fib of 30. Okay, 59. All right. I'm assuming you're sharing the screen. Let's see the difference. Instead of 11 million, wait, what is this? 1 million, right? 148,000. Now we only went inside the code 59 times. See how brilliant this is, right? Just even from a performance perspective, instead of 10 power 6, we are at 10 power 2 or 10 power 1, right? This is your optimization. Now, I know we haven't reached the actual definition of dynamic programming, but the reason for that is, let's go back to the screen, broadcast. Okay, so now if I ask you the same question, sure, your first intuition was, let's optimize it by adding a cache. Now, I want you to optimize this more. Earlier, in all the recursion functions, when we saw recursion, we said, sure, it's a terrible idea in itself. It's a decent thing, at least we are using a cache, but what is optimization to? What did we say earlier is the best way to optimize recursion is? I'm sorry if there's a chat window. I'm not seeing it. Okay. Okay, so what is the best way to optimize any recursion code?
The one that we discussed, like
Yeah, so
memoization.
we already did, like we have cache, right? Memoization. But I'm saying, okay, recursion itself by definition is a mess.
Mm-hmm.
So earlier, remember when we were doing factorial of n, we started with recursion and then we did something to make it simpler, faster. Chris, this was the answer you gave earlier. So the question earlier was, hey, you have recursion, what is the best way to optimize it? So this is going back to our class 1 or 2. The answer is best way to optimize recursion is just make it iterative. That's it, right? So remember, we started with the most complicated solution, which is here we tried recursion, and we saw that it takes close to 1 million calls for the same function. Then we added your first intuition, which is, oh, this is overlapping subproblems. So we added a cache, and it went to the total number of count was 59. Now, let's think why did I always insist iteration is better than recursion, right? So when we had the stack frame here, we are in main, and recursion is where it like fib of 4, fib of 3, and every time this happens, it was creating newer and newer stack frames. But instead, if you do iteration, it will simply just stay here for int is equal to the very first stack frame, maybe the second one, because from main, the control goes second stack frame. So now, in a way, we are optimizing the space also, right? The sheer amount of stack frames that's created is majorly reduced. So if you remember, this was the same idea which we saw in the class of what thing called factorial of n. So now we do the same thing. We go back to our same code, right? Now, how can you convert a recursive function into iterative public static int fib n? So if I ask you this, the core functionality. So what is the core functionality? 0, 1, 1, 2, 3, etc. Indexes of the Fibonacci 0, 1, 2, 3. If you are at index 3 and somebody tells you the previous 2 values are done, what will you do? I know it's the same answer you gave earlier, Ulrika. For int I, so we just sum it up, right? So sum for me is same thing, cache of n is equal to cache of n minus 1 plus cache of n minus 2. Now, then we haven't even written the for loop, that's okay. Then we go to step 3, which is what is the base or exit condition? The exit condition is, oh yeah, we have to check if n is equal to 0. We're going to hard code it as cache of n is equal to 0. If n is equal to 1, I'm going to say cache of n is equal to 1. Same code as before. Now, for int I is equal to 2, because you already have values for 0 and 1, index 0 and 1, so this and this is done, I less than cache dot length I plus plus. And we are done. That's it, we are done. See the beauty of it? We started with the most complicated thing, recursion. We switched it to iteration. And just by doing that switch, we realized, oh, wow, okay, we are going to save a ton of these values, right? Because all we did was take recursion and we built it back out thinking, oh yeah, recursion is a boring thing. Now, believe it or not, this is dynamic programming. That's it. That's it. So you don't have to think about anything more. Dynamic programming is nothing but one, we start with recursion. Then we add 2 memoization, and 3, we optimize our initial memory part, the overlapping subproblems with memoization, right? Now we optimize recursion with iteration. That's it. Welcome to dynamic programming. See, once you knew the fundamentals of recursion, how simple this is, right? And in fact, you can actually try it out yourself. If you start putting the count values, we are probably out of time to show that. If you start seeing the count values, you'll realize it goes to like 5 or 10 or something instead of 59. So remember 1 million, it went to 59, and from there it's going to go to 5 or 10 because there's no more stack frames created. There's no more recursive functions. Now, the last parting gift, the parting shot, Parthian shot, question is, you might have seen this question before. There are steps, right? There are n steps, and the person is starting here. He can either do one step at a time or 2 steps at a time. Let's say you are at n equal to 10. How many different ways? This is a standard dynamic programming question. So how many different ways can you reach 10? Is it clear? Like the person can do 1, 1, 1, 1, 1. So that'll be 10 steps. Or he can do 2, 2, 2, 2, 2. That'll be 5 steps. Or he can decide I'm going to do 9 ones or 8 ones, and then I'm going to do a step of 2. So at the outset, this might look like, oh my God, I have no idea how to do this. But one thing, if you remember, is every dynamic programming problem is a Fibonacci series. It's just like the Fibonacci series problem. So here, all you have to do is public static int number of ways, int n, that is the value 10 which is coming in here. Okay, same logic. And just remember the same thing we said, cache of n is equal to number of ways of n minus 1 plus number of ways of n minus 2. See this part, this is exactly the Fibonacci. And that's it, you're done. Never ever think or open it up. If you start opening it up, your brain cannot understand. Our brain is a linear processor. It doesn't have stacks, so it cannot clearly understand a stack. But if you know the simple trick of going back to recursion and realizing, oh, everything is the same thing, number of ways to get to n minus 1 plus number of ways of getting n minus 2. And all you have to do is copy paste this thing again, right? We can even start writing recursion, the same step we did, take the overlapping subproblems and all that stuff. But if you're so thorough with Fibonacci, you're done. You don't have to, you're done with dynamic programming. You can go to Geeks for Geeks and start trying out the easy questions. All right, we're out of time. Let's stop here. Do you have any questions? So your homework is 1, try out the number of steps. And 2, the easy questions in Geeks for Geeks. And 3, I'm sure you'll encounter this. This is called coin exchange problem, which the question is, if you're given $10, how many different ways can I get to 10? 5, $4, and $1. Maybe I'll do 5, 3, 2. So this, etc., etc. This question might look so complicated, but this is exactly like this, right? Okay.